and the linear velocity is replaced with angular velocity omega. In place of linear momentum, it is half p square by m. Here, half L square by I. The work, it is a force and displacement here, tau into theta, just replacing the parameters. Work energy theorem, here half I omega 2 square minus half I omega 1 square. The rotational power in linear motion F into V, and here it is tau into omega. The angular impulse. In linear value, the F into dt, here tau into dt, it is nothing but the change in angular momentum. And keep in mind the Newton's second law of rotatory motion. It is a very, very important concept. And we can replace that tau with I alpha like m into A. And here L equal to I omega like m into V. Very good concepts. We can, based on that concepts, go through some important questions. A solid cylinder of mass capital M and radius r is rotating along its axis with angular velocity omega without friction. A particle of mass m is moving with the velocity v, collides against the cylinder and sticks to its rim. After the impact, calculate the angular velocity of the cylinder. And keep in mind the initial concepts before the collision. Intuitively, the initial momentum of the cylinder is I omega, and for the particle mvr, linear momentum into perpendicular separation. But by the application of conservation of angular momentum, before and after they are same, so L1 should equal to L2. But after the collision, what happened? And that mass particle sticks to the sticks to the cylinder, and hence we can say that I plus m into r square into omega, and hence we can say that omega is equal to I omega mvr by I plus mr square. A good question is waiting again. A light rod carries 3 equal masses ABC. What will be the velocity of B in the vertical position of the rod if it is released from horizontal position? So, the loss of the gravitational potential energy is equal to the gain in kinetic energy. So, here the rotational aspects we have to think. So, for each particle, what is the moment of what is the loss of gravitational potential energy, we have to find it. So, for the first particle, keep in mind just L by 3 loss, but for the second one 2 into L by 3, but for the third one as L. So that is a very important concept. Then the gain in kinetic energy for the rotational effect. So half into I omega square. What is I? A rod with a length, say we can say L by 3, 2L by 3. Yes, so we can easily that mass particle, a mass particle m at a separation L by 3, and hence we formula m into L by 3 square. And the second one at a separation 2 into L by 3, and third one at a separation L. So simple formula. You get the value for omega, but we need to find what is the linear velocity for the B particle. So we can write as V equal to omega into LB. Just a substitution, you get the answer. A very good question. A flywheel assumed to be a ring of mass 0.2 kilogram and radius 10 centimeter is rotating with 5 by pi revolutions per second about an axis perpendicular to the plane passing through its center. Calculate the angular momentum and kinetic energy. So simple formulas, you get the answer. But how we can find omega? 2 pi into frequency. Good concept. We are waiting a very good previous year question. If the rotational kinetic energy of a body is increased by 300%, determine the percentage increase in angular momentum. And keep in mind, we can't use our error relation here because that are applicable only for a few values less than 10 degree percentage increment. But here it is 300%. So, and the change in value by, or the final value minus initial value by initial value into 100%. So what is the final value here? Before that, angular momentum is proportional to root E. And 300 percentage increment. So E1 plus 3 times of E1. So the final value become 4E. So you can just substitute and get the value. The power output of an automobile is advertised to be 200 horsepower at 6,000 rotations per minute. What is the corresponding torque? The torque is the power by omega. You can just substitute the concept. You get the answer. Two disks of the same moment of inertia rotating about their regular axis, passing through center and perpendicular to the plane of the disk with the angular velocities omega 1 and omega 2. They are brought into contact face to face, coinciding the axis of rotation, the expression for the loss of energy during the process. By using the conservation of angular momentum, before we can write as I1 omega 1 plus I2 omega 2, but after they join together, so I1 plus I2 into common angular velocity omega, we can find easily omega. Then what is the change in kinetic energy? The initial kinetic energy is what? Half I omega 1 square plus half I omega 2 square minus. What is the final angular velocity, kinetic energy? Half into. The moment of inertia is 2I into omega square. You get the answer. A solid sphere of mass m and radius r is rotating about its diameter. A solid cylinder of the same mass and same radius is also rotating about its geometrical axis with an angular speed twice that of the sphere, the ratio of their kinetic energies of rotation. And here, at first one, the solid sphere, the formula half I omega square I is 2 by 5 mr square. But for the second case, it is a solid cylinder, so the moment of inertia take the value as mr square by 2. But a difference is there. Its angular velocity is double that of the solid sphere, so you get the value 1 by 5. Rolling motion. We can wait one question in minimum for every exams. A very important topic. The linear motion plus the rotatory motion together, we can say the rolling motion. But here we needed to find the rolling without slipping. The rolling without slipping. Keep in mind the velocity at the point of contact of the rolling body with the surface is 0 here and is called the pure rolling. And there we can say as V is equal to R omega. It is a very, very important relation. Keep in mind there is no relative motion between the surfaces at the point of contact. Between the surfaces. Therefore, the work done against the friction becomes 0. Look, if a body is performing rolling, then the velocity of any point of the body with respect to the surface is given by, due to the linear motion, VCM, due to the rotatory motion, that is a very important one, omega cross R. Look, here, the linear motion, every particles are moving with the same velocity. But here it is the rotational motion, and hence we can say here every particles are under circular motion. So tangentially its velocity goes on changing. It is a very important concept. And hence we can say, see, what is the net effect? If you just consider the highest point, there are two contributions, one from linear and one from rotation, and hence its value become the very important concept as 2V, and here it becomes V, and here it is 0, but here it becomes root 2 times. It's a very important concept. While considering the kinetic energy, see, we can think two different ways. If you give importance to the linear velocity, we can just substitute for I is equal to mk square and omega equal to v square by r square. You get a very good relation as a half mv square into 1 plus k square by r square. And keep in mind the k square by r square, actually it is the nature of the body is revealed with that term. If m into k square equal to mr square for a ring, there k square by r square become 1. But for a solid sphere, m into k square take the value as 2 by 5. So you get the value as 2 by 5. But in another concept, you can, if you just substitute In place of v is equal to r omega, then you can take that half into mr square plus I into omega square. We can write as a half is equal to ip omega square. Ip is the moment of inertia about this point. And keep in mind, we can replace that rolling motion about the center of mass by the rotational motion about the point of contact. That means the rolling motion about the center of mass is equivalent to the rotation about the point of contact. Likewise, we can easily to find the velocity at this point. About this point, it is at a separation 2r, and hence the velocity at that point is nothing but 2 into 2r into omega. So you get the value 2v. That is a good concept, the very important one. The very important another concepts, the fraction of kinetic energy associated with the translation. The kinetic energy translation by total kinetic energy, half mv square division by half mv square plus half I omega square. You get the simple concept as 1 by 1 plus k square by r square. The fraction of kinetic energy associated with the rotation, the rotational kinetic energy by the total kinetic energy is equal to half I omega square by half mv square plus half I omega square. In simple formula, k square by r square by 1 plus k square by r square. The kinetic energy rotation by linear, take the value. See the rolling motion along the inclined plane, and we are waiting with the 4 important concepts. The minimum coefficient of friction needed to roll down for an inclination theta is tan theta by 1 plus k square by r square. The velocity at the bottom of an body when it starts from rest from the top of h, that value is root 2gh by 1 plus k square by r square. The acceleration along the inclined plane as g sin theta by 1 plus k square by r square. The time of descent, take the value as root of 2s by g sin theta into 1 plus k square by r square. Keep in mind here s is the length of the inclined plane. Look the some shortcuts. If different bodies are allowed to roll down an inclined plane, the body with the k square by r square will least value will reach the body first, the maximum last, and if they are equal, then they will reach together. If you just compare the rolling and sliding, for a smooth inclined plane, the velocity at the end to point is root 2gh. So we can easily relate that rolling velocity is vs for sliding by root 1 plus k square by r square. Similarly, acceleration during rolling is equal to during sliding by 1 plus k square by r square. Similarly, the time. So this is a very important concept. We can move with some few questions, very, very good questions. A thin hollow cylinder slides without rotating with a speed v and rolls with the same speed without slipping. Find the ratio of kinetic energy. So linear motion, sliding means, so half mv square. Rolling, we know half mv square into 1 plus k square by r square. But here a hollow cylinder, so its moment of inertia is equivalent to a ring. So mk square equal to mr square, k square by r square become 1. So that is the answer. When a sphere of moment of inertia rolls down an inclined plane, then find the percentage of rotational kinetic energy of total energy. So rotational kinetic energy by total energy is nothing but k square by r square by 1 plus k square by r square into 100%. For a sphere, 2 by 5 for k square by r square. You get the answer. We are waiting a good question. A solid sphere rolls without slipping on a rough surface, and the center of mass has a constant speed v0. Find the angular momentum of the sphere about the point of contact. The two motions are there. So two contributions are there. One linear and one rotational effect. So it is nothing but for the we can say as L center of mass. So we can say that is equal to I omega. Simple formula. So I is what? 2 by 5 mr square. Omega we can write as v square by r. Then how we can find the direction? So you just using the right hand thumb rule, you get the concept here. and is rotating like this one, so inward by using the right hand thumb rule. And similarly here the linear momentum, so that is like this one, so r into the linear momentum, so m into v0 r, you could just add that together, you get the points. So we can move to the last question, a good question, a good application of rolling motion. A fixed pulley of radius 20 centimeter and moment of inertia 0.32 kilogram meter square about its axle has a massless cord wrapped around its rim. A 2 kilogram mass capital M is attached to the end of the cord. The pulley can rotate about its axis without any friction. Find the acceleration of the mass M. At first we can just use the equation of motion. So the weight mg is acting vertically downward, the tension upward, but it is moving coming downwards, so 2g minus d is equal to 2 into a. But for the pulley, because of that tension, it will act as the tangential force to it, and hence it is under rotatory motion. So we can substitute as a tau is equal to t into r equal to I alpha. So, but we know for the rolling body a equal to alpha into r, a equal to r alpha, and you can substitute for t, and you get the answer. So students, it's a very very important chapter that try to do maximum MCQs, especially in different regions like moment of inertia, the rigid body dynamics, especially torque, angular momentum, conservation of angular momentum, and the rolling. And we can wait minimum 3 to 4 questions from this chapter. So God bless you. Take care. Thank you.